Time travel remains one of the most captivating subjects, bridging science, philosophy, and speculative inquiry. In this discussion, we explore the rigorous theoretical frameworks that underpin the possibility of traversing time, examining advanced mathematical models and experimental evidence with a relaxed yet precise tone. Although time travel is often portrayed through fantastical narratives, our focus is on an expert-level analysis that delves into the interplay between space-time geometry, quantum dynamics, and relativistic effects. Over the past century, our understanding of time has undergone a transformation, from Newton's concept of absolute linear time to the modern view that treats time as an integral dimension interwoven with space. With general relativity reconfiguring notions of gravity and causality, scientists now consider phenomena such as time dilation, closed time-like curves, and wormholes to be more than mere curiosities. In our exploration, we examine not only the theoretical groundwork laid by Einstein and his successors, but also the rigorous mathematical constraints imposed by modern physics. We will review precise numerical simulations, differential geometry, and tensor calculus that help define where theoretical loopholes might exist. Our analysis is grounded in fact-driven research, drawing on quantitative studies and advanced experiments that probe the limits of temporal manipulation. This discussion will also highlight the role of exotic matter with negative energy densities, a critical ingredient in several hypothetical models, as well as the challenges associated with scaling these concepts from mathematical abstractions to physical reality. By combining historical insights with modern experimental techniques and theoretical advancements, we aim to provide a comprehensive, yet technically detailed, narrative that addresses whether time travel could ever transition from theory to practice, all while maintaining a relaxed, friendly tone that invites rigorous debate and further inquiry. In order to appreciate the modern scientific debate on time travel, it is instructive to trace the rich historical evolution of the idea. Early human cultures frequently touched upon the concept of altering the flow of time, with myths and legends portraying gods and heroes who could manipulate fate and chronology. Ancient texts often depicted cyclical views of time, where past, present, and future blended into an eternal recurrence, hinting at the possibility of revisiting previous eras. As human thought progressed, these philosophical musings found expression in literature and art, gradually evolving into a staple of intellectual inquiry that would later inform scientific theories. During the Renaissance and Enlightenment, emerging thinkers began to interpret time in a more structured manner. Although early scientists largely followed Newton's notion of absolute time, the philosophical seeds for challenging linear temporality had already been sown. The profound shifts came with the advent of Einstein's special and general theories of relativity at the beginning of the 20th century, which recast time as a dimension intertwined with space. These revolutionary ideas introduced the concept of space-time, a mathematical construct where time is as manipulable as the spatial dimensions. Pioneering research into Minkowski space-time laid the groundwork for envisioning scenarios where time might loop back on itself, leading to the formulation of closed time-like curves. Subsequent works explored how curvature and gravitational effects could create regions of spacetime that support paths deviating from conventional temporal flow. Such theoretical breakthroughs have spurred ongoing debates, as scientists scrutinize whether these mathematical constructs have any practical physical realization. These historical milestones underscore the transformation from mythological speculation to rigorous scientific inquiry, establishing a continuum in which modern researchers seek to fuse historical intuition with experimental precision. The integration of cultural narratives with scientific evolution continues to inspire debates and theoretical advancements in the field of time travel research. At the heart of the scientific discussion on time travel lie the fundamental theories of modern physics, among which Einstein's theory of relativity stands preeminent. General relativity posits that gravity is a manifestation of the curvature of spacetime rather than a conventional force. This geometric interpretation allows for non-intuitive phenomena such as gravitational time dilation, wherein clocks in stronger gravitational fields tick slower relative to those in weaker fields. The mathematics of space-time curvature, particularly the Einstein field equations, reveals solutions that permit exotic configurations, including the possibility of closed time-like curves, CTCs, paths through spacetime that loop back onto themselves. Such curves could, theoretically, allow an object to revisit its own past, though at the expense of introducing significant conceptual and mathematical challenges that demand a careful and quantitative approach. Beyond the framework of relativity, the concept of a wormhole emerges as a logical extension of these ideas. Wormholes, formerly known as Einstein-Rosen bridges, are theoretical passages that connect disparate regions in spacetime through a tunnel-like structure. While the equations admit their existence under restrictive conditions, maintaining a stable wormhole would require exotic matter with negative energy density, a phenomenon supported by certain predictions in quantum field theory, but not yet observed in large-scale systems. Detailed numerical models indicate that any such exotic matter must be carefully balanced to prevent instability, as even minor deviations could cause the wormhole structure to collapse. Complementing these relativistic models, quantum mechanics introduces additional layers of complexity. Certain quantum gravity proposals suggest that closed time-like curves might naturally emerge in the quantum realm, whereas other interpretations imply that quantum fluctuations could generate transient channels resembling miniature wormholes. The challenge of unifying general relativity with quantum mechanics, exemplified by competing theories such as string theory and loop quantum gravity, further complicates the search for a coherent theory of time travel. Both approaches invoke intricate mathematical machinery, ranging from complex manifolds to perturbative expansions, to explore if and how macroscopic time loops might be reconciled with the probabilistic framework of quantum mechanics. Researchers employ differential geometry, tensor calculus, and sophisticated computational simulations to examine the stability of these exotic spacetimes. Such studies include analyses of perturbative corrections to the field equations and exhaustive examinations of potential violations of energy conditions. Overall, while the established theories offer tantalizing clues, each model is burdened by significant mathematical and experimental challenges that must be surmounted to feasibly propose time travel as more than a theoretical possibility. In recent decades, exploration into the possibility of time travel has evolved from purely theoretical musings to a domain bolstered by sophisticated experiments and high-precision observations. Advances in experimental physics have allowed scientists to test predictions, such as time dilation effects, under extreme conditions. For example, high-speed particle accelerators routinely confirm that particles moving at relativistic speeds experience slower aging processes relative to stationary observers, providing quantitative support for aspects of Einstein's theory. Similarly, satellite-based atomic clocks demonstrate measurable time differentials as a function of both velocity and gravitational potential, reaffirming that time is a dynamic variable amenable to precise measurement. Modern research has also embraced quantum systems to simulate aspects of curved spacetime. In controlled laboratory settings, experiments with trapped ions and superconducting circuits have been specifically designed to replicate conditions reminiscent of wormhole physics on microscopic scales. Though these analogs do not demonstrate macroscopic time travel, they offer critical insights into how quantum coherence and entanglement might be preserved in scenarios featuring closed time-like curves. By integrating data from astronomical observations, such as measurements of cosmic microwave background anisotropies and galaxy distributions, cosmologists are piecing together the large-scale topology of the universe, which indirectly informs models of temporal anomalies. One particularly intriguing research avenue centers on the elusive concept of exotic matter. Based on predictions from quantum field theory, negative energy density appears in phenomena like the Casimir effect, where quantum fluctuations generate an attractive force between narrowly separated conducting plates. Extensive experimental efforts are underway to accurately measure these forces and ascertain whether, under specially engineered conditions, macroscopic amounts of negative energy could be harnessed to stabilize a wormhole throat. International collaborations have emerged to study high-energy astrophysical events and simulate extreme gravitational fields, aiming to understand if transient closed time-like curves might occur naturally in cosmic settings. In addition, recent advancements in numerical simulations have enabled researchers to model complex gravitational systems with unprecedented accuracy. These computer models integrate data from particle accelerators, astronomical surveys, and quantum experiments to produce a cohesive picture of how spacetime might behave under non-traditional configurations. Although many technological challenges remain, ranging from the precise control of energy densities to the robustness of artificially created quantum states, the cumulative experimental evidence continuously informs theoretical refinements. Taken together, these modern approaches underscore a persistent, data-driven commitment to rigorously testing the boundaries of what our current physical laws might allow in the realm of time travel. The prospect of time travel is inextricably linked with a series of paradoxes that challenge our conventional understanding of causality. Among the most notorious is the grandfather paradox. If an individual were to journey back in time and inadvertently prevent the existence of their own progenitors, the logical inconsistency would undermine the very premise of time travel. Such paradoxes are not merely thought experiments. They compel us to reconsider foundational principles of cause and effect and the robust conservation laws of physics. Advanced theoretical models have introduced the concept of causal loops, where events in the future influence the past, creating self-consistent but non-intuitive trajectories. Proponents of the Novikov self-consistency principle argue that any actions taken by a time traveler must align with the established timeline, effectively precluding any outcome that might generate a paradox. However, these proposals hinge on precise mathematically defined conditions that many find improbably restrictive when weighed against the stochastic nature of quantum phenomena. In addition to the grandfather paradox, other logical challenges, such as the information paradox present in black hole thermodynamics, point to potential violations of unitarity and entropy conservation. These paradoxes force physicists to re-examine the very underpinnings of temporal symmetry and the arrow of time, urging a closer look at how quantum systems process and retain information. As our theoretical frameworks become more refined, any valid model of time travel must robustly address these paradoxes, offering explanations that are both mathematically consistent and experimentally verifiable. The logical challenges presented by these paradoxes serve as both a warning and a guide, insisting that any pathway to practical time travel must resolve inherent contradictions without sacrificing the integrity of established scientific principles. Within the expert community, time travel theories elicit both enthusiasm and skepticism. Critics argue that the extreme conditions required, such as the existence of exotic matter with negative energy density or the precise manipulation of spacetime curvature, are so remote from current technological capabilities that they may forever remain theoretical constructs. Many models predicting time travel arise from highly idealized solutions to Einstein's field equations, which, despite their mathematical elegance, may not correspond to realistic physical environments. Alternative perspectives emphasize that quantum fluctuations and the uncertainty principle might inherently disrupt any attempt to maintain closed time-like curves over macroscopic scales. Recent analyses have suggested that the inherent probabilistic nature of quantum systems could prevent the stabilization required for a functional time machine, thereby preserving causality. Attempts to incorporate time travel within frameworks like string theory or loop quantum gravity have met with inconclusive results, further fueling skepticism. Proponents of these critiques assert that while the mathematics allows for the possibility, the physical realization of these conditions remains unverified. Ethical and philosophical considerations also contribute to the alternative viewpoints. The potential consequences of altering historical events or generating self-sustaining causal loops invoke a host of ethical dilemmas that many argue would be unacceptable even if the technology were available. Until experimental evidence can reliably demonstrate the existence of traversable wormholes or substantiate extensive negative energy densities, a significant portion of the scientific community remains firmly cautious, viewing time travel as an intriguing theoretical exercise rather than an imminent technological breakthrough. In conclusion, the scientific exploration of time travel presents a fascinating blend of advanced theoretical physics, rigorous mathematics, and experimental ambition. Our discussion has navigated through the evolution of time travel concepts, from historical narratives and transformative insights from relativity to intricate quantum models and modern experiments, revealing a rich tapestry of ideas grounded in precise numerical and fact-based analysis. Despite tantalizing theoretical constructs suggesting the possibility of closed time-like curves and wormhole solutions, enormous technical, mathematical, and empirical challenges persist. The interplay between exotic matter properties, advanced computational models, and stringent energy conditions underscores that any viable time travel theory must overcome significant obstacles. Future breakthroughs in quantum gravity, high-energy astrophysics, or unforeseen technological innovations might eventually bridge the gap between theory and practice, offering deeper insights into the nature of time and space-time. Yet, the challenges associated with engineering the precise environments necessary for time travel remain daunting. Ultimately, while time travel may currently reside within the realm of theoretical possibility and controlled laboratory simulations, its study continues to drive progress in both physics and mathematics. The ongoing commitment of the scientific community to probe these deep questions reaffirms the human pursuit of knowledge and the relentless inquiry into the fabric of the universe.